Hello, we will now do the 7-1 worksheet. So I encourage you to work this along as I'm doing it and to pause the video and to try the different problems and then check your work as I work through it. So this is 7-1, which is just the basic concept of what a sampling distribution is and the terminology surrounding it. So let's look at the first context. So this says a forest ranger manages a forest that has 12,787 pine trees in it. He wishes to estimate the mean number of pine cones that are in each of these pine trees. Unbeknownst to him, the mean number of pine cones for all 12,787 of the trees is 77.4 with a standard deviation of 12.7. The ranger takes a simple random sample of 50 of the trees and gets a mean of 76.9 and a standard deviation of 13.2. Identify the following. So the main part of this problem is identifying what are these different numbers, what do we call them? Okay. And so in the terminology surrounding this. Okay. So first of all, what is the population? It's the whole group we want to know something about, in essence. It can be people, animals, or things. And in this case, if you think about it, it is all the pine trees in the forest. So we would say the population is all 12,787 pine trees in this forest. That is the whole group that we want to know something about. And the parameters, in essence, what we want to know. And in this case, we got, parameters are just numbers that describe the whole population. And so we really have two of them listed here. We have the mean and standard deviation. So the mean, which called that mu, is a mean of a population, and that would be 77.4 pine cones. It doesn't have really a units here, like feet or seconds or anything, so we just leave it like that. And so the other parameter, the other number that describes a population, is the standard deviation, which is sigma, and that's 12.7. So what is the sample? The sample is the subset of the population that we actually study. And of course, it's critical for us that it gets collected randomly, which this one did. So it is the 50 selected trees. That is what is in our sample. And the statistics are the numbers that describe the sample. And so we have the mean of 76.9. That is an X bar. X bar is a sample mean. So that'd be 76.9. And then the sample standard deviation, we say is S. S is equal to 13.2. And of course, this X bar is an estimate of the mu. We're using that to estimate mu. And then S is an estimate of sigma. Okay, because in future chapters, we aren't going to know these numbers. The only way we could know them is by doing a census. And so we're going to use these as estimates. So what is the population distribution? A distribution is a list of numbers and how often they are taken. All right. So this is the population distribution is just the numbers in the whole population. So in this case, it is in what we're interested in is the number of pine cones. That's what we're measuring. So it is the number of pine cones in each of the 12,787 trees. Okay, so the population distribution is just 12,787 numbers. Okay, if you listen to the whole thing, it'd be that many numbers, and it's the number of pine cones in each tree. What is the sample distribution? It's every number that is in the sample. So it is the number of pine cones that are in these 50 trees. So it is the number of pine cones in each of the 50 trees in the sample. That is a sample distribution. Now, I'm sorry, I didn't have that where you can see it. So, so that is what a sample distribution is, the number of pine cones in each of the 50 trees in the sample. Now, what is a sampling distribution? A sampling distribution is every value a sample statistic can take. Like in our sample in this problem, we got 76.9, but we realize this is just one of many X bars I could have gotten. Okay, and if I took another sample of size 50 and averaged those numbers, I would get another X bar. And so let me explain the concept of a sampling distribution is. First of all, what is the population distribution, that's just every number in the population. So their mean, by the way, is 77.4. And so it's all these 12,787 numbers. So if I put an X for every one of them, there'd be 12,787 X's. It's just every number in the population. Okay. So there's 12,787 X's in our population distribution. Our sample distribution is every number in the sample. And there's 50 of them. Their mean is 76.9. So they are centered around 76.9. And so you have a bunch of X's, not X bars, X's. Okay. And there's 50 of them, 50 X's. So there's 50 X's here that are in our sample. That's our sample distribution. Our sampling distribution is every value X bar can take. There's one of them. They will be centered around the population value, 77.4. They'll be centered around that. So our first X bar was 76.9. So that's somewhere down here. Its X bar means it's an average of a bunch of numbers. In this case, 50. Our sample size is 50. So we average these 50 numbers in that X bar. If we found 50 more numbers and found another X bar, and then 50 more numbers, found another X bar, average those 50 numbers. We kept going and found more values of X bar, repeated sampling, all of these, and theoretically there's an infinite number of these, or it's all possible combinations of 50 from that, which there's a limited number there, but it's a very big number. All the possible values of X bar, and that's what we call a sampling distribution. Now, and as we talk about in 7.2 and in 7.3, this is going to be approximately normal because our sample size is bigger than 30 for a mean. So it will be approximately normal. So having said all of that, what is a sampling distribution? A sampling distribution is this. It is every value that the sample mean X bar can take in repeated sampling of sample size 50 from this forest, from the same population, same sample size, same population. It's every value X bar can take. Whenever you get an X bar, you should always say to yourself, this is just one of many I could have gotten. Okay. And all the possible ones are what we call a sampling distribution. Okay. Number 8. And so it says, draw the graphs of 4 different sampling distributions of sample means, one with low bias, low variability, then with high bias, high variability, high bias, low variability, and then one with high bias, high variability. So, all right, now unbiased means this, like this would be an unbiased measure. So if your X bars, and I explained this in the video in section 1, unbiased means this. Unbiased means the mean of all these X bars is equal to mu. And that's what's happening here, is that these X bars are equaling mu. Okay, so that's what bias is. Variability is when they're really spread out. So this would be low bias variability, low bias, because look, these X bars average. The mean of the X bars appears to equal mu. So there's no bias. And they're really scrunched together. So that's low variability. And so this would be low bias, high variability. So it's low bias because the mean, if you average these X bars, they appear to equal mu. So the mean of the X bars appears to equal mu, but they're really spread out. So that's high variability. Okay. So then we have this. We have high bias, low variability. Okay. It's low variability because they're all scrunched together, but it's high bias because the mean of the X bars is not equal to mu. When you average these, it's not equal to mu. So that's a bias situation. Whatever we're doing a bad job of collecting data here. Okay, because my X bars are systematically too low for the mu. And then we have this high bias, high variability. The numbers are really spread out, so it's high variability. The mean of the X bars is certainly not equal to mu. And so that is a bias situation. Now, 1 or 2 of the X bars may be close over here, but the average of the X bars is not equal to mu. So that is pictures of high bias. And that concept and those drawings are popular things on the AP exam. So let's look at the next problem. So the context part 2 is this. It says the ranger in part 1 also wants to estimate the proportion. So now they're dealing with a proportion of the 12,787 pine trees that have bird nests in them. Unbeknownst to him, 62.7%, 8,021 of the 12,787 have bird nests in them. The ranger takes an SRS, a simple random sample of 200 of the trees, and finds that 118 of them, 59%, have nests in them. Identify the following. So this is what, there's two main kinds of problems we're dealing with pretty much the rest of the year. One that deals with means. So this one deals with the mean. You know, that should really stand out to you. We're dealing with a mean. So we're dealing with mu's and x bars here. And that is we're gonna discuss that more fully in section 7.3. And then in 7.2, we talk more about proportions. So those are the two main kinds of problems. So what is the population here? Well, we have the same who or what do we want to know something about? And so that is all 12,787 pine trees in this forest. That's the whole group we want to know something about. What is the parameter? Parameters are numbers that describe populations. Okay. And so in this case, it's a proportion. And so in this case, it says, unbeknownst to him, 62.7% of the trees have bird nests in them. So that would be a P. The parameter is P, which is 0.627. So you can express that as a percent at 62.7%, or you could express it as a fraction, that over that, or you could express it like this. Most of the time you'll see it expressed like this, and that's the way I tend to do it, but it doesn't matter. You can do it, you know, in either way. All right. So the sample is the subset we're actually studying, and there's 200 of them that we're actually studying. So our sample is the 200 selected trees. What is our statistic? Our number that describes our sample. Well, when in proportions, our statistic is going to be a p hat. And so our p hat is 59%, 0.59. Okay. All right. Trick question here. What is the population distribution? Well, the population distribution will be every number that's in the population. And there isn't one here. Okay. There, with proportions, there is not a population distribution. With means, there is. With means, every tree has a number associated with it. All right, so you get all these different numbers. But when you're dealing with a proportion, either they have a bird's nest or not. And so that's a categorical situation. There's really not a number associated with it. So there's no numbers in the population, so to speak. The number is just in a proportion for the whole thing. It's not like every tree has a different number. Same thing with a sample. It's not like all 200 of these trees have a different sample. They have a different number. They either have a bird's nest or they don't have a bird's nest. So it's a success failure situation. It's categorical. There is no sample distribution. There isn't one. So there isn't a population distribution or a sample distribution with proportions, okay? But there is a sampling distribution. The sampling distribution is every value p hat could possibly take. So what it is that we took a sample and our population proportion p, it says is equal to 62.7%. So that is equal to 0.627. And we took a sample of size 200, okay, and we got 0.59. Well, that p hat was somewhere down here. Now, the concept of a sampling distribution, once again, if we took another sample of size 200 and found another p hat, it would be different from this one just because of random chance, or what we call sampling distribution. And if we took a third sample, we could find a third p hat. If we took a fourth sample, we could find the proportion in that, and so forth. And if we took all possible samples and found all possible sample proportions, all possible p hats, that family of p hats we call a sampling distribution. Sampling distribution, okay? And as we're going to discuss in section 2, it'll be approximately normal as long as n times p and n times 1 minus p are greater than 10, but we don't have to think about that now. What is the sampling distribution? Well, I've just written it out here, okay? It is every value that our sample statistic, our sample proportion, p hat, could take in repeated samples of size 200 from this same population. That is what the sampling distribution is. Every value p hat could possibly take. And then one more question on this worksheet. It says this. It says the ranger wishes to have a sampling distribution that has less variability than the one in the context above. In other words, he wants to be confident that his statistic is very close to his parameter. So that's the ideal thing. Going back to the means, before I answer this question, we like this situation. We like low bias. We like it when our X bars are bunched together really close to the mu. And so the way we prevent bias is by getting a random sample. The way we prevent too much variability and being too spread out is this: have a large sample size. The bigger sample size leads to less variability. So more than likely, this one had a huge sample size. Had a very small sample size. And that makes, see, high variability means it has a small sample size. Small sample size. So we want our p hats to be really, we want to get them really in tight to the p. We want very little variability. And so when that happens, we can be confident that our p hat, if our sampling distribution looks like this, so we don't know which one of these p hats we're getting, but we can be pretty confident that our p hat's going to be close to b because of the large sample size. Okay, and so that's the answer to the last question, is that how should he decrease his variability, have less variability, less spread, increase his sample size. A smaller sample size means the p hats are going to be spread out. The smaller sample size, the larger sample size is going to bunch them together. We'll talk specifically how big that we need our sample size to be later in the chapter and also in future chapters. Notice there's no bias here. Okay, this is unbiased situation, because the mean of our p hats is in fact equal to p. Okay, same thing here. The mean of the p hats appears to be equal to p. So there you go. So that's your little 7-1 worksheet. Thanks for paying attention. If you have any questions, please send them to me.